Okay, so welcome back to another video. So here we have another interesting Fibonacci infinite sum, and we have the infinite sum starting with our index n equals 0 of 1 divided by f sub 2n plus 1 and then plus 1. So you might be thinking of how we might start off something like this. Well, the first and really the only important formula we'll be using to start out this entire formula is actually using Binet's formula for Fibonacci numbers. I did a whole derivation of that, so if you want to check that out, the link's in the description below. And to add a little further more to it, that I actually did the same thing for Lucas numbers, that you can also check the same thing, but totally unrelated, but for your viewing pleasure, if you want to, I'll leave that in the description as well. So Binet's formula we'll be using to do that substitution, evaluate at the 2n plus 1 term instead of the nth Fibonacci number. Then it just involves with a bunch of algebra simplification and all that stuff, typical algebra stuff from there. And a nice little series that to close it off that you can observe from there once we get to that step. So other than that, let's actually just jump right in. So to recall, Binet's formula is written at the nth Fibonacci number is equal to, in terms of the golden ratio number, phi to the power n subtract 1 minus phi to the power n, and then all this being divided by the square root of 5. So to make things a little bit easier, we're going to actually replace the input of our 1 minus phi with a different identity. So note the following, that 1 minus phi is equivalent to -1 divided by phi, so the negative reciprocal of the golden ratio number. So that will be substituted back here. So now let's evaluate this at the 2n plus 1 term of the Fibonacci number. So we substitute that in, that will yield us, so this will be phi to the power 2n plus 1, then subtract, replace this with -1 divided by phi, then evaluate this, well, then to the power 2n plus 1, not evaluate, we're not just yet, all this being divided by the square root of 5. So there's some things we can actually do a little bit of simplifying over here, as you can tell. Okay, so now next what we have to do is distribute the 2n plus 1 exponent into our input over here. We have a -1, so that's something alternating over there, but eventually what's nice is that it actually just cancels out when we simplify things a little further. What I mean by that is now taking one step close, taking things a little slower and simplifying out. So I'll have now the following is going to be phi to the 2n plus 1, then subtract, then put out the negative here, -1, then to the power 2n plus 1, and then multiply with 1 divided by phi to the 2n plus 1. And of course, this all still being divided by the square root of 5. And we can actually, again, simplify even further that for 1, it's a -1, there's a negative here, I'll distribute that into here, so now that becomes a 2n plus 2. But if we're dealing with index for n equals 0 and then all the way up, so 0 and all the natural numbers, that means for whatever you plug in into here, it's always going to be an even degree, and -1 to an even degree is always going to be +1, so that actually just disappears from there. So now, leaving us left was just phi to the power 2n plus 1, then add this with 1 divided by phi to the 2n plus 1, and then divided by the square root of 5. And so with this now, we have 2n plus 1, evaluate the 2n plus 1 term for the Fibonacci number here. Let's just add that 1 back, so that way we can achieve what we need to. So f to the 2n plus 1, then now plus 1, so okay, so going back to over here as we evaluated, so it's phi 2n plus 1, then add this with 1 divided by phi to the 2n plus 1 divided by square root of 5, then add this with a whole +1, so we can actually, do a little bit of simplification. That now we can actually multiply in order to get rid of the denominator from here, so just multiply phi to the 2n plus 1 to both the numerator and denominator, so yielding us with phi to the 4n plus 2 plus 1, then divided by the square root of 5 multiplied by phi to the 2n plus 1, add this with 1, then we can simplify that even further just so we can get a common denominator over here, but that's actually easy to see that we'll have now phi to the 4n plus 2 plus the square root of 5 multiplied by phi to the 2n plus 1 plus 1, all being divided by the square root of 5 multiplied by phi to the 2n plus 1 term. So that's great. And so therefore, now going back to the series, well, before we actually do that, so now putting this back, so I have 1 divided by 1 divided by f to the 2n plus 1, and then add this to 1, so basically just flip the reciprocal. So let me actually, for neatness, let me write the denominator out first. So 4n plus 2 plus the square root of 5, then phi 2n plus 1, add this with 1, and then our numerator is going to be the square root of 5, then 5 to the 2n plus 1. Let's actually take the summation of both sides with our index just like that. So now that actually is one step closer to yielding our goal. So that means so far the infinite sum n is equal 0 of 1 divided by f sub 2n plus 1 is indeed equivalent to the infinite sum n is equal 0 of the square root of 5 times phi to the power 2n plus 1, all this being divided by phi to the 4n plus 2, plus the square root of 5 phi 2n plus 1, and then add this with 1. So now the whole goal is we need to figure out how to evaluate this term over here. So how do we do something like this? To make things a little bit simpler, let's actually do a little bit of a substitution. We'll substitute x equals phi to the 2n plus 1. And so what that concurs to is, now ignoring the summation symbol for later, because we'll get to that eventually. So now we'll have the square root of 5 multiplied by x, then divided by x squared, add this with the square root of 5 times x, and then add this with 1. Okay, so now we have to simplify this out. So what does that come down to? Nice trick. Of course, I think you can see that we can actually apply some partial fraction decomposition, and you'll see that the denominator actually reduces down nicely such that we have two products. The product being, so let me first write this out, square root of 5x, then x squared plus square root of 5x plus 1. Now we have to figure out our terms. So capital A, the denominator for 1 reduces down to x plus phi. And then the second term, so B, is x plus 1 divided by phi. Okay, so now we can actually apply that partial fraction decomposition over here. So now the square root of 5 times x is equal to a, and then multiplied by x plus 1 divided by phi. So X basically just drew the butterfly method. Add this with b, then multiply with x plus phi. So now to make things a little bit easier, again, you can actually distribute all the terms, but let's actually set this up in terms of a systems of equations. So if I set everything for the x coefficient of terms, so x, so a, and then b, so we have a plus b is equal to the square root of 5, and then for the other one we have a divided by phi, and then add this with b times phi is just equal to 0. Okay, so we have to figure this out. To make this a little bit simpler, now let's actually multiply phi to this equation over here just so the denominator cancels here. So in other words, that's the same thing as, now let me actually draw the arrow to the second equation, not the whole thing. Now I have a, and then add this with b phi squared equals 0. Okay, so with this, now we can say that if I want to reduce this so that I get a variable by itself and do the substitution easily, so we can see that now I have that a is equal to negative b phi squared. So we'll actually put that substitution back into here, and then putting that back in, so I have now negative b phi squared, add this with b. In other words, that's the same thing as if I just factor out the b, so I have b, then multiply with, now I'm just going to put the positive out first, so that's the positive here, and then minus, so 1 minus phi squared, and then set that equal to the square root of 5. What's nice is that we can actually reduce this to another little identity to say that this is the same thing as the negative golden ratio number. Substitute this back in, and then if I just divide the negative golden ratio number to both sides, so we already have our b terms, so that means b is indeed just equal to negative square root of 5 and then divided by phi. So now I just plug this back in for b, so negative b, so rather now the negatives cancel, so square root of 5 times phi squared divided by phi. So in other words, now we have that a is just equal to the square root of 5 and then times phi. And so therefore, going back to over here, so let me put this arrow over here. Going back to here, just plugging in our a and b value. So this will yield us the square root of 5 times 5. Then we just divide this by x plus phi, and then subtract the square root of 5 and then divided by phi times x plus 1 divided by phi. And then let's just substitute back our x that we did the substitution over here, then back into here. So now we'll actually yield the following. So the square root of 5 times 5, then divided by phi 2n plus 1 plus phi, then subtract the square root of 5 and then divided by phi, multiplied by phi 2n plus 1, and then plus 1 divided by phi. So we can actually reduce this even further, so that's even great. So what we notice is, for one, that I'll factor out a phi over here from the denominator, and that's nice that it actually cancels the numerator of phi as well. And then another thing is we'll just distribute the phi over here just to get rid of that denominator right here. So performing all this, and so we'll have the square root of phi and then divided by phi 2n, then plus 1, then subtract the square root of 5, then multiply or divided by the phi to the power 2n plus 2, and then add this with 1. And so therefore now going back to here, so then therefore continuing forward, that's now the infinite sum n equals 0 of the square root of phi divided by phi 2n plus 1, then subtract the square root of phi, then phi 2n plus 2, and then add this with 1. Okay, so now lastly, all we have to do is now let's actually expand this term out. So let's actually put down a couple numbers. So what's great is that now let's do things one at a time. So the first term we'll have is, first I'll have the square root of 5 divided by 2, then subtract the square root of 5 divided by phi square plus 1. Add this, so now do this for the n equals 1 term, so square root of 5 divided by phi square plus 1, then subtract square root of 5, then phi to the 4th plus 1, then add this, same thing, so now do this for n equals 2, so phi 4 plus 1, subtract 5, or square root of 5, and then divided by phi 6 plus 1, and then the list just keeps going on, so forth, and you'll notice that we're going to have some terms that cancel. This is going to cancel out, cancel out, cancel out, cancel out, cancel out, cancel out infinitely, so on and so forth. So you can guess that this is indeed a telescoping series, and so therefore the final answer of this entire thing indeed is just equal to just the square root of 5 divided by 2. Or in other words, if you want to be fancy with it, you can actually write this as the same thing as phi subtract 1/2. And so therefore that completes this yet another amazing Fibonacci infinite sum, using the Binet's formula for Fibonacci numbers as a starter to evaluate this entire process just like that. So yeah, that's pretty cool if you ask me.